Hi folks, and welcome back to Physics with Captain Rod. Making this video to be an example of an AC circuit problem involving, fairly standard household wiring here. So in this example, we're going to imagine, we're in our bathroom here, I guess, and we're going to talk about the currents involved and the cost to run these three things: a pair of 60-watt light bulbs and a 1600-watt hair dryer at the same time. Now, we're going to be assuming, standard US power grid, which is an AC source with a peak of 170 volts and an RMS voltage of 120 volts. The reason why I put two of them here is to discuss just general household wiring. So we're going to imagine here that our hair blower here is, maybe plugged in here. And again, in any sort of power cord, there's two wires. And, if you actually cut it open, look, one of them is going to go to like the small outlet and one to the larger outlet. Now, the light bulbs are probably, they're probably wired into the walls. You're not going to actually plug them in. But ultimately what that means is still this. That they are connected like so and like so. So what I mean ultimately is, even though they may not be plugged into the outlets per se, they're direct wired. It's just like there were outlets in the way. That part doesn't really matter. So what these things mean, where's my pen? What these things mean here and here are that these items are all now plugged into the power source at the house. Ultimately goes to the circuit box. Right now, the circuit diagram. So we have an AC voltage at 120 volts. That's the RMS voltage for the US power grid. Now I'm also going to include a breaker here. I'm just going to make a box here for my breaker. Right, if you go, if you live in a house and you go and open your breaker box here, this would be one of the circuit breakers. And then all of this stuff now is wired in parallel. Right, household wiring is all in parallel due to, so that you have constant voltages everywhere. So for the first light bulb here, I'm going to go ahead and put a resistance. I'm going to call it, let's just call it R1 here, and I'll call that light bulb 1. My pen is giving me a little trouble here today for some reason. All right, for the second light bulb, I'm going to put an R2, call that bulb 2. Now what we're going to do here is we're going to go ahead and put the another resistor here for the hair dryer. So this is an R2, and I'll just put RD, I guess, for dryer. So the circuit diagram would look something like this. Any circuit diagram you draw for household wiring will look similar to this. It's all, everything that you plug in are all in parallel with a 120 volt voltage source, and they should have circuit breakers. Now this thing right here, what it is, a breaker means that in this case, we're going to assume a 15 amp breaker. Most circuit breakers are either 15 or 20 amps, the overwhelming majority of them. And it's not part of the circuit per se, in that it doesn't have a resistance or anything that we have to worry about. The idea behind the breaker is if the current in this part of the branch hits 15 amps, the breaker shuts the circuit down. Maybe not right at 15, maybe 15.1 or something, but that's the idea. 10 amp current is okay, 20 amp current not okay. So what we're going to do now is we're going to go through and kind of analyze this circuit. Now, if you've seen my videos on voltage, you've seen that I always like to talk about the constant potentials. Now it is true that the voltage, if I pick a spot here, the voltage is constantly changing, because remember, in an AC source, we're talking about a sinusoidal voltage source, meaning if I plotted it, looks like this. So half the time the voltage is going to be, basically pushing current in one direction, half the time the other. But at any instant in time, this is all conducting material. So at any instant in time, this is an equipotential, because these are all wires made of copper. So I'm going to go ahead and color code this. And same thing on the other side. This is all conducting material as well. So this is an equipotential right across the breaker, by the way. The breaker will not affect that because it too is essentially conducting material between there. I mean, you might get a tiny little voltage drop, but in theory, approximately zero. So a very important thing to realize, right, when you look here, red to black, right, the voltage of 120, red to black, is good there. It's good in all of these locations. So what that means is we can apply Ohm's law, voltage equals current times resistance, across both resistors and the dryer. Now, we don't know voltages here. What we know are wattages. So there's other equations I can write here. One, power is current times voltage, right? It's also equal to current squared times resistance. And what we know are powers. So let's go ahead and use the 60 watts for the light bulb equals current times voltage. And for the voltage, we're going to use 120 volts, right? Because that's the RMS voltage of the US power grid. So what we're going to get a current of, if we take 60 watts and divide by 120 volts, we get 0.5 amps. Now, unit-wise, it works out to watt over volts, but a watt is a joule per second, and a volt is a joule per coulomb. So this works out to coulomb per second, or amps. So what that means is, in this branch right here, we're going to have an average current of 0.5 amps. So I'm going to go ahead and label that. All right, we got 0.5 amps. And although I don't see this much, I'm going to go ahead and just put it like so, with kind of a double arrow here, if you will. Because the current, you know, that's an RMS AC current, means that the current is half the time in one direction, half the time in the other. The second bulb has the same wattage, so we're going to have the same 0.5 amps. Okay, and now let's talk about the hairdryer. All right, so I'm going to use the same formula here. Power is current times voltage, except for the hairdryer, our power is 1600 watts. Again, at the same 120 volts. That's a very important fundamental here. That's why household wiring is in parallel like this, so that the voltages are the same, anything that you plug in. So now we're going to get a slightly larger current here. I get about 13.3 amps. Wow, it's going to be close. Now, here's kind of how current works. We've got 0.5 amps here, 0.5 amps here, and 13.3 here. Now, the first 0.5 is good anywhere along here. The second 0.5 along here. The third 0.5, or I'm sorry, the 13.3 is good here. This part of the circuit right here is supplying all of that. So the current in this part of the circuit, I'll just leave this in green, is the sum of the three, and that ends up being 14.3 amps. And, you know, is that going to blow the breaker? No, but it's close. A 15 amp breaker would be fairly close here. And for those of you, you know, if you run hair dryers a lot, if you had a couple more lights going on here and you ran that 1600 watt dryer, you probably would trip the breaker. Now, bathrooms, maybe a lot of them have 20 amp breakers. I guess I'm not sure. I'm sure a lot of these are wired with 15s, but anyway, this one turned out to be pretty close to tripping the breaker. All right, let's talk about cost per hour to do this. Of course, you know, you probably won't run the hair dryer for an hour, but humor me. So our total power output here, if we had the two lights and the hair dryer running, would be, what would that, 1720 watts? Now, you're not charged by the watt, you're charged by the kilowatt hour. So written as a kilowatt, this is one, come on pen, 1.72 kilowatt. Kilo means 1,000. If we multiplied it by an hour, we would get 1.72 kilowatt hour. And now what I'm going to do is just multiply that by our cost times 16 cents per kilowatt hour. Notice the units cancel. And what do we get out of that? I get about 27.5 cents. Approximately 20, let's just say approximately 28 cents is good enough. So, just meant to be kind of an introductory video on how to work simple circuit problems for AC circuits and simple household wiring. I hope that this has been a good example for you. Have a great day.